Hello, calculus fans. We're going to talk about some related rate problems, which once you get a good flow for these, a good feel for them, really some pretty rewarding problems, kind of some cool things. These are fairly basic and but should give us a good feel for where we're headed. I'm going to skip around here a little bit. Some of these that you have on your handout, if you have this handout, are a little bit redundant, but practice never hurts. So here we go. Let's take a look at number 2. We have oil spilling from a ruptured tanker that spreads in a circle. You might not need to draw the diagrams. I like having the diagrams. Circles really only have one dimension to them, and that is the radius. That spreads in a circle on the surface of the ocean. The radius of the spill increases. The radius of the spill increases, so that is one of the things that we know is that the change of the radius versus change of time, or dr dt, is increasing, so positive 4. So we like to list the things we know. We also want to try to eventually put down what we want to know. And then we create a snapshot, as I refer to it. You'll see what I'm talking about here. How fast, so that's what is the rate that the area is increasing. So what we want is the change of area over change of time, or dA dt. When the radius is 14, that's what I refer to as the snapshot. The radius is constantly changing. The circle is just constantly getting bigger and bigger and bigger, but at one point the radius of the spill is 14 meters. That's our snapshot. So we've got area that links our radius together, so we're going to go area equals pi r squared. We need a formula that links the things we know with the things we want to know. So if I take derivative with respect to t of both sides, I get dA dt equals pi times 2r dr dt, or 2 pi r dr dt. And now, once we've done that derivative work, now we can put our snapshot in. We got a snapshot where the radius is 14. I wouldn't want to put it in here, then I'm taking the derivative of a constant. And I've got dr dt is 4, so dA dt is 2 pi times a snapshot 14 when dr dt is 4. So we have equals 28 times 4. Let's go. I'm 28. My tough brain day today. We have 112 pi is dA dt. Now we just have to get the units of measure together, and the units of measure were in meters. This is area we're talking about changing, so that's meters squared per minute. And we got that one. Then number 3 talks about a cube growing. I'm actually going to do number 6 a little bit later. That would be very, very similar to it. I'm choosing it because it has the cube shrinking, but no real other reason. I'm just trying to give you a feel for the different problems within this worksheet. As you can see, number 4 is an awful lot like number 2 that we just did. So I'm going to jump to this conical paper cup, number 5. We've got a 20 centimeter tall with its 20 centimeters tall, radius of 10. The cup is being filled with water. So if the cup's being filled, our conical cup, if gravity's in play here, looks something like this. It is always radius 10. That's not a snapshot. And the height is always, 20 centimeters tall. And what we typically do with that, in fact, by typically I mean just about every time we've got a cone problem, is we're going to relate our radius to our height. And I notice in this case, radius is to height as 10 is to 20, or radius is to 10 as height is to 20, so radius equals 1/2 height, or height equals 2 radius. And I like to write them both down on these cone problems, because chances are in our volume formula later on, I'm either going to substitute 1/2 H for R or 2R for H. So conical paper cup is 20 centimeters tall, radius 10. That's all we've really worked with so far. The cup is being filled with water so that the water level rises. That's our height. So one of the things we know is change of height over change of time is it's rising, so positive 2. What we want to know is at what rate is the water being poured into the cup. That is volume. We want to know dV dt. So I need a formula that ties volume of a cone in with its height. Well, here's our volume formula. Volume is 1/3 pi r squared h. That's our volume of the cone. However, I'm really not interested in dealing with r here. I could take the derivative and then I'd have a whole product rule with r and h, and I have dr dt's, dh dt's, and really I just want dh dt and dv dt. Therefore, I'm going to, in place of r equals, I'm going to put in 1/2 h. Volume equals 1/3 pi times 1/2 h squared times another h. Just substitute. And let's see, volume equals, that would be 1/4 times 1/3, 1/12 pi h squared times h cubed. And now we can go for dV dt. I'll put it right here. dV dt equals 1/12 pi is all just a constant coefficient. So 1/12 pi times 3h squared dh dt. And now we can do our snapshot since we've done the derivative. Our snapshot is poured into the cup when the water level h is 9. We just want to have a height of 9, or a height of 9 here. That's our snapshot value, h. So we get dV dt is, let's see, I'm going to just take 3 times 1/12, 1/4 pi times h, 9 squared, 81, dh dt, but dh dt at that moment is times 2. So I get dV dt is 2 times 1/4, 1/2. We get 81 pi. 2 reduces 4 to 2. 81 halves pi, which of course we could ... change that into a decimal. But what are we talking about here? Volume. Therefore, our units are centimeters, volume cubed per second. Okay. Alrighty, so number 6, again, I said we had another hypothetical cube shrinking. I said that on the first page. So let's take a look. Here we've got a cube, and a cube equal on each side. One of the better cubes I've drawn in my lifetime. A cube shrinks at a rate of 64 meters cubed per second. So what we know is the volume, dV dt, is, if it shrinks, I'm going to put negative 64. At what rate are the sides of the cube changing? Well, if it's a cube, then this side is x, this side is x, this side is x. At what rate we want to know what we want to know is what rate of the sides. We want to know how fast is x changing with respect to time. So now we need a formula that ties volume of a cone in with x's. Well, of course, that is volume equals x cubed. And I want to know this when the sides are 4. The sides aren't always 4. That is our snapshot. I don't put 4 in until I take the derivative. dV dt is 3x squared. dx dt And now I can put my snapshot in, and it says, at what rate are the sides of the cube changing when the sides are 4 meters each? So 3 times 4 squared. I want to know dx dt, but I know dv dt is negative 64. So what do we get? We get dx dt equals negative 64 divided by 16 times 3, 48, or negative 4/3. That's our x, that's the length, so that is just plain old meters per minute. It's not an area, not a volume. And now, we want to be careful with that negative, because if they asked, at what rate are the sides of the cube shrinking, then we would just say at 4/3 meters per minute. At what rate are the sides increasing, that would be negative. And when it says changing, we should really include that negative there. They are getting smaller, and changing doesn't necessarily imply getting smaller. All right, let's move along here. Number 7. A spherical snowball. Toughest thing about the spheres might be just making certain that we know what the formulas are for volumes and areas when necessary. We've got this spherical snowball. And a sphere really just has that one radius to be concerned with. Is rolled in fresh snow, causing it to grow at a rate of, guys, that's our volume of the snowball. It's in cubic. It's in cubic inches. So what we know is that the volume is changing with respect to time at a rate of 36 pi. How fast is the radius changing? What we want is dr dt. And what do we have that ties volume in with radius in a sphere? The volume of a sphere is 4/3 pi r cubed. And I think we're good. We got a snapshot. How fast is the radius changing when the radius is 2, click. There's our snapshot. I'm going to put 2 in for radius, just not yet. dv dt is 4/3 times pi times 3r squared dr dt, or dv dt is 3 times 4/3, 4 pi r snapshot 2 squared dr dt, or let's see, dv dt is constantly 36 pi equals 4 times 4, 16 pi dr dt. dr dt is 36 pi on 16 pi. Let's see, we can reduce by 4, we can reduce by pi, we get 9/4. dr dt is 9/4. R is the radius, radius is a length, so we're just plain old inches per second. There we have it. Here's a conical paper cup, and I would refer you back to number 5, very similar. Let's take a look at number 9. An observer stands 2,400 feet away from a launch pad to observe a rocket launch. 2,400. Doesn't sound like that's going to change, so might get away with using a constant there. The rocket blasts off and maintains a velocity of 200 feet per second. Assume the scenario can be modeled as a right triangle. So I'm going to call, so we're rocket blasts off, right triangle. I'm going to call this length y, just because it's going up and down. And what we know is the rocket blasts off and maintains a velocity. What we know is that dy dt is 200. Assume the scenario can be modeled as a right triangle. How fast is the observer to the rocket distance changing? They're looking for this right here. I'm going to call it r. There's our distance here. How fast is it changing? And as the rocket goes up, that is clearly getting longer. And when the rocket is 700 feet from the ground. And when the rocket is 700 feet from the ground, there's our snapshot right there. Y isn't always 700, but 2400 is always 2400. So at our snapshot, it might be worth going Pythagorean here. Let's see, I get second square root of 2400 squared, and you might recognize this one already, plus 700 squared is 2500. So we also have a snapshot at 2500. There's our snapshots right here, values we can put in for R or for Y after we do the derivative work. So I need a formula that relates R to Y, and you could probably get some angle measures in here and talk about that with trigonometry, but I'm going to go Pythagorean. And here's what we've got. 2400 squared plus Y squared equals R squared. And I've got some snapshot values, R and Y. Do I put those in there now? Nope, not until I've taken the derivative. Let's see, how fast is the observer to the rocket distance changing? What we want is the change of R with respect to time. Okay, so let's go ahead, dr dt these. Here's good news. Derivative of a constant, even a big one, is 0. So we get 2y dy dt equals 2r dr dt. We can reduce both sides by 2, and we can put some snapshots in. How fast is the observer to the rocket distance changing when the rocket's 700 feet from the ground? So we got 700 dy dt times 200 equals r 2500 dr dt, what we want. Dr dt is, let's see, that would be a 14 with 4 zeros divided by 2500, and let's just go ahead and, well, I guess we can do this, equals, cancel, 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 1400 divided by 25, and we get 56. Dr dt equals 56. R is just a distance, so plain old feet per second. Okay, this is helping. And let's take a look at one more. Water leaking onto a floor forms a circular pool. Just for fun, just for fun and practice, I'm going to give myself a good circle here, hopefully. Not bad. I could do better. I could do better than that. You've probably seen me do better than that. A little bit embarrassed by that effort. Here we go. So we've got R, leaking on the floor in a circular pool. The area of the pool increases. There we go. What do we know? The area is increasing. That's dA dt. At a rate of 49 pi on the area. How fast is the radius? We're talking about radius later. I'm just going to call this on the area pi r squared. I mean, that's the area, right? Okay. How fast is the radius? What we want is dr dt. How fast is the radius changing when r is 4? Click, snapshot. When r is 4. So our area is, how fast is the area? Is pi r squared. dA dt is 2 pi r dr dt, what we're looking for. dA dt, pi's cancel, is 49 on r squared. When r is 4, dr dt, kind of riding uphill here for some reason. So we get dr dt equals, let's see, it was 49 on, this could be a 4 as well, 16, and we need to multiply or divide. We could divide, but multiply by 1 on 8 pi to get rid of the 8 pi. 1 on 8 pi, or we get 49 on 128 pi. Our unit for radius is a length. Our unit measure is centimeters per minute. And of course, we could go to calculator with that and make a little bit more sense of our answer. Hope that's helpful. Pretty quick little video on a little bit more than half of the assignment. Let me know what I can help with.